When glancing at a hastily scribbled number, your brain recognizes it instantly. You don't consciously analyze the ink, you just know what it is. But computers don't have that intuition. When a machine looks at that same piece of paper, it doesn't see a number. It sees a grid of tiny squares, simply logging which spots have ink and which are empty. For decades, programmers tried to teach machines to read by giving them a strict checklist of rules. The logic was rigid. If there is a straight line across the top and a diagonal line moving down, the computer marks it as a 7. That works for perfect printed text, but human handwriting is full of quirks. We loop our letters, slant our lines, and rarely follow perfect geometry. Those rigid rules simply can't keep up with the way real people write. Think about how many people cross their 7s. That extra stroke isn't on the checklist, so the rule fails. It rejects a perfectly legible number. Now imagine a page where every number is unique. You could never write enough rules to cover every human variation. To understand the messy real world, computers needed a different approach. They needed a flexible architecture that learns patterns rather than just following a script. To find that flexibility, researchers looked to biology. After all, animals navigate a complex, unpredictable world every single day without a single line of computer code. This map of neural pathways in a mouse brain shows the inspiration for a new kind of machine. Instead of isolated rules, these brains use massive, interconnected webs of cells that work together to recognize the world. Taking that biological web and translating it into software led to the creation of artificial neural networks. This diagram shows how the software is built. The first layer looks at raw data, identifying dark pixels. By passing information through deeper layers, the network combines these tiny edges into complex shapes, finally recognizing a digit. This process of building complexity step by step is the key. It's how a machine transforms a collection of meaningless dots into a clear, understandable concept. This grid of digits is a classic training set. Starting as a blank slate, the network learns through trial and error. It guesses the number, checks the correct answer, and fine-tunes its connections to be slightly more accurate next time. Instead of giving a hard yes or no, like the old rule-based systems, the trained network gives us a percentage. It measures how much a scribble looks like a 7, allowing for a healthy margin of error. After seeing enough variety, the network transforms from a disorganized web into a highly tuned system for recognizing patterns. This makes the system incredibly resilient. Even if someone's handwriting is nearly illegible, the network doesn't freeze up in confusion. It simply makes its best guess based on the patterns it has learned. This technology had an immediate impact on our daily lives. Early versions allowed post offices to automatically read scribbled zip codes, sorting mail far faster than any human operator could. Today, those same concepts are used to digitize ancient manuscripts, power our search engines, and even build tools that read text aloud for people who are visually impaired. This shift is what finally allowed our digital tools to adapt to the messy reality of human life, rather than forcing humans to adapt to the rigid logic of computers. Even our best models are still approximations. Training these networks takes massive amounts of data and electricity, while a biological brain navigates the natural world using less energy than a dim light bulb to solve tasks that are vastly more complex. But by borrowing nature's blueprint, we finally taught our machines to see the world as we do, not as a series of rigid rules, but as a rich,